Okay. And I I formulated the condition, necessary and sufficient conditions for any transformation from, so formulated necessary and sufficient condition for any transformation, rho h to sigma h. Okay, and now we'll so today I will prove the condition and will apply. So the condition was in terms of these diagrams. Apply the condition to apply the condition. For example, to get formula for extractable work of formation, and more generally for such processes where I have initial state, I add some work, and then so I have two states, and the question is how much work should I add to get this transition. Good. So so now I want to prove start with this to prove the so let me recall the condition was that rho h can go by thermal operations to this if and only if this diagram of rho is always above the diagram of sigma, right? So let me what I did, I already. So what we can do, only we have to conserve energy. So our unitaries will be without fixed energy block. And within this block, I showed you the structure of levels. I showed you the structure of levels. So the structure of levels was the following. So here is the in my old drawings, entropy of system was here the smallest and here the largest, and the entropy of energy of reservoir was going down in this way. So was going here I had large energy of system and smaller, and here I had small energy of reservoir and larger. So then so I picturize it like this, in this way. Yes, so you have here large, let me write it, large ER, oh sorry, small ER, large ER, and also here large ES, small ES, but because its energy is fixed, the sum is fixed. Sum is fixed, just the energy, right? So I have now what I can do arbitrary. I can do arbitrary unitary in this space, but it's because we have only followed only diagonal states. Then it's enough to reshuffle. Then it turns out that it's enough just to consider only some permutations of the levels. So first, let me tell that what I can do, I can do more. I can do arbitrary mixture of unitaries. So this is because later I will trace out in reservoirs. I will just sum up this, sum up this, sum up this. So even though I can do only unitaries, effectively I can also do mixture of unitaries. How I do that? So suppose I want to make unitary which is say 1/3 of U1, and so with probably 1/3 I want to do U1, and with probability 2/3 I want to do U2. So what I do, I just divide this. So this is this 1/3, this is 2/3. And then, so I divide all these blocks into proportion of 1/3 to 2/3, right? So here you have 1/3 of levels, and here you have 2/3 of levels. And I apply unitary U1 to just these green blocks. So I permute on the levels within the green, and then I apply U2 to red ones. Right? So this is essentially, I use the fact that you have essentially really huge heat bath and plenty levels of them, and I can generalize these probabilities by just using the randomness from the heat bath. So I have really a lot of randomness here, and I divide this into this. And so, and within each block, the probabilities are equal. So if I divide in this using this ratio, I get that this unitary will be performed with probability 1/3. This was 2/3. So actually, I can. So when I trace it, when I sum it up, it will be really like a mixture, even though the whole looking as a globally to this, we see that there's just one unitary. Yes, I do some permutation within green and some permutation within red. So this is one unitary, no random. I do not apply any random transformation, but because I will sum up this, finally it will be precisely the same effect as if the transformation was random. And now now it's a good situation, because we know we have a criterion when we can go from some state to some other state by random permutations. It is majorization. So that was what was the main tool in this thermodynamics for kids. Right. So now, if we take this if we take some initial state of this R and S for this fixed energy, we can ask, well, to what other state we can go by mixture of unitaries. So by mixtures of permutations, right? So if we can answer this, then we will later trace out the reservoir, and then we'll have an answer. So to what state we can go? So let us apply majorization criteria. Okay, so this is we know this is equivalent to this. Okay, when this majorizes, standard majorization. So this is standard majorization, which, let me recall, it was this, that for all L should be greater than this one. These are eigenvalues of this, and these are eigenvalues of this. Right? So let me apply this, but here these states have very particular probabilities. So look, so these probabilities are all equal, and then they are, let me call what they were. So these probabilities were, it was P of this larger times, and so that was from the system, and times something coming from a heat bath, which was just it was divided by this dimension 1. This is the dimension times E2 minus beta ES1, and so on. Right? So this is these are the probabilities. So we see that these probabilities have very special structure, and then if we will apply this, we will maybe be able to simplify it, not just stayed on this level of these big things. So let me now make some something to simplify notation. Okay, but so first let me write how how these all probabilities look like, how this full probability distribution looks like. So it looks like the following. From this block, we have, so let me say, rho RSE actually is diagonal of what? PE1S divided by the E2 minus beta ES1. And there are how many of them? There are D times E2 minus beta of them. So we see that probabilities come in such bunches of equal probabilities, and this gives the hope to simplify this original very general majorization. So this is the first block. Then from the second block, we go from the second block right second, which is E2 now, right? D. So they differ just by the label of the system energy, right? So it's here D times E2 minus beta E2S, okay, and so on. So we have these blocks. Then what we should do, in order to apply majorization, we need to order them. Here we need to order these probabilities in a standard way. But you recall that in defining these functions, I required different ordering. That was beta ordering, so I didn't order these p's, but p divided by this, by this thing. So now you see here how it comes out, because when I apply a standard ordering to these probabilities, then I do not order these, but I do order, this D factor is all the same, all the way the same, so I just order these quantities, right? So now you see that this, here we have, we will get this thermal ordering rather than standard ordering, even though on this level it's just ordering. So to apply majorization, sorry, here I should add this, yes, so they should be ordered. Order. Okay, so to apply majorization, we need to order these probabilities. So we simply, and we see that these are all equal. So ordering is really reshuffling the whole such bunches, right? So within the group you have equal probabilities. So looking at if I draw the histogram of these, so you may have here bunch of these first, then you may have these, then you may have such bunch, and so on. Right, so this can look like here. So that now ordering is really these clusters. So now that we order, which is I put this here, right, and so on. So such it goes in these bunches. Okay, good. To simplify notation, I propose to call this ordered. Oh, now I ordered this. So it's not E1 but EI1, which means that this is this guy. This is this largest one, which is not the first one. So I propose nevertheless to just right. So this for the ordered if I order these quantities, but I then write that this is P1 to the minus beta E1. Yes, so let me repeat. Neither Pi's are ordered nor energies are ordered. Yes, so E1 doesn't mean that the energy is largest. P1 does not mean the probability is largest. But what it means that this ratio is largest. Because here we order these probabilities, not just these things. Good. So then, so once I did it, let me note one thing, that because this D we will take very large, the heat map will be very large, very many of these levels. Therefore, these quantities are terribly small. So there are extremely large number of these. So this is now misleading a picture. These all will be very, very, very small and very many of them. So we will go from summation from these summations, we'll go to just integrals, right? So we can draw this now a different kind of histogram, where area will be probability. Okay, we'll draw it in such a way that the area of the so how to do that? So this thing. So but this will be 1 over d. This very small thing. This will be P1 over E2 minus beta E1. So you see now this, if I this multiply with this, I get precisely the probability, right? And there are how many of them? There are how many of them? Well, this is the number of them. Okay, and then I go with this. So this is always standard. This. And then I have. So what happened is that, what I want to that the majorization criterion is to compare some. I should insert some other index. It is some index. Okay, the L. So some J equal to 1 to L. So I want to, let me call these probabilities somehow. Okay, these are these probabilities. There are many of them. You know, I have to label them one by one. So this will be first, second, and so on and so on and so on. So this L, so these are the probabilities. So this L goes from 1 to, and this is the first group. Then we have the second group plus okay, until I have all groups, so it is D times 2Z. So L goes through so many. So therefore, a natural change of is that I will go from 0 to Z dx, right? And the function that I'm going to here to integrate is just this step function. So if you simply give me some L from here, it will point out some L. So the thing is, so I want to integrate these. So I want to sum up these, but because this is very tiny, then it amounts to really integrate from 0 to some x x0, that is simply L divided by D will be x0. So simply, so this will go to, sorry, it's not to Z, but just to L divided by D, yes, which will be this x0 that I have here, right? So okay, so then my majorization condition turns out to be that it will be so this is some step function. Let me call it just f tilde of rho, and the majorization is now that for any x0 from 0 to Z, I have this the rho of x dx should be greater than this f sigma x dx. Okay, but of course now these integrals, because these are step functions, so then you see that these integrals, when this so this step function is defined, it has some special points here where there are jumps, and this point, so what's that? What is this point? So this is this divided, so it is these many of them, I divide by d, so I get that this is e2 minus beta e1. And this is e2 minus beta e2, and so on. So then now it's x axis. So then you see that if you just integrate this function, you get simply you put these points here. So you get linear interpolation. So from this you will get first linear function, and from this you get another one, and another one, and another one. So this is our function, precisely our function f, that is written here. So okay, I write this. So that gives. And also let me. So how this f was defined? So it was defined in such a way that here I put this e2 minus beta e. So this is, we are done, and let's see what's here. So here is here. So what's here? So this is the area of this whole thing. The area of this whole thing is p of this thing is p1 divided by this times this, which is e2 minus beta e1. So you see that here I have precisely p1 what I wanted. Yes, and then now because this was ordered, which means that I have to I have ordered really these quantities, joint quantities. Therefore, I do not put here standard order, but this beta ordering p1 and e, and energies are here put by means of beta ordering. Good. So that's how you prove this criterion. And now let us see how it works to compute some thermodynamical some quantities. So as I said, we want to go, say, from rho to w. We want to go from w to sigma, and we want to go finally this way or this way. But as I said, this it can be the same if you put here work to be both negative and positive. Right. So so therefore it is convenient to ask. So to answer these questions, what is maximal work that I can draw and so on, it's good to compare two situations. What's a diagram of such a thing, and what's a diagram of such a thing? Because these are the main objects that we will have here. So how did I? So versus the original diagram, right? Good. So.
Can I ask a quick question? Since you just finished up this section. So to implement these transformations, you need to make use of these permutations in which you distinguish the bath states.
Yes.
Which, when we normally think of thermodynamics,
yeah,
that's a lot to demand.
Yes, that's paranoid. Yes, that's.
So.
So why is this thermodynamics?
Really essential, or is it?
Yeah. So now there is this parallel work of Johann which shows you that it's that at least this thing you can do without really distinguishing states of the heat bath. But we have some work in progress whether this thing you can do. So there is this Egloff paper, but they still use thermal operations. So in their paper, still you have to have really distinguished levels or states of the heat bath. And it looks like you hit some wall that some of these transformations you may not be able to do with some very crude operation. But this is still not clear. Well, the only thing you may hope that, so what I believe now is that for some transformation, you will need some non-Markovian coupling, which means that you really have a memory of some region of the heat, but it's not a large region. So that's one may hope.
In a similar direction, suppose we can exactly distinguish the thermal state. So say we can implement a U up to some approximate value epsilon. Then is this result is still valid within the same?
Yeah, here we assume that you can do anything. So.
Yeah, but like suppose we can't do exactly.
Count.
Cannot.
I cannot.
Yeah, but we can only do the approximately.
Mm-hmm. So when we try to do this by some more crude operations, so when you make some approximation, then usually you get that you can put approximate on your state. So you can do still exact transformations, but you can have a state which is not exactly like you thought it was. And then you simply apply to the quantities that to these diagrams, to the function f, you simply apply some smoothing. So you add this error to these functions. And in particular for drawing work, you get that then the result, the amount of work you can draw is not, say, this d mean, this mean relative entropy, but is smooth version. But we were not happy. We were not quite happy with this, and I will just say something more about small errors. I hope to manage. Good. So we need to come. So is that okay? Yeah, I'm good. So you mean whether the state rho is diagonal?
Yeah.
So in this case, the formula that we obtained from these diagrams is true also it's just for any state, and then you do not have this problem. You just look at the diagonal, and you have to use the diagonal. For these, is harder. So we have some of the partial results where the state is not diagonal, and then if it is not exactly diagonal, then you have to apply these partial results, which is still at very beginning stage.
Instead of using the diagonal elements, the whole trace is just the diagonal.
Yeah, for this you just use the diagonal elements. So you have like super selection rule, because their output is work which is defined with respect to only diagonal, which is good. So it's nice to compare this, and that. So let's start. Let me draw here some generic diagram for rho, which is this, and that. Okay, so here you have, oh, maybe it should be greater. Z1, big. Okay, so that's F rho. Now, so it has 3 levels. So let's now take this state. So that's the work system. So we have has 2 levels, and that has 3 levels. So all together we have 6 levels, and the levels have these energies. Okay. So we have now 6 levels. So therefore, the thermodiagram for this thing should have here 6 sections, right? But look, this state, rho tensor 0, it actually occupies only these. only these occupied by rho tensor 0, and also also if you look at that, only these are occupied by rho times. So both these diagrams for this and for this will again have just 3 sections, because if this is on these diagrams, if you have probability 0, if you have some probability 0, then diagrams look like that, and then you are simply here. That's how it works, because here you put just you add up probabilities, and then at the end you add these probabilities that have 0. So then we look at them and we say, look, when we draw a diagram, we order these things. P. We have to order these. Okay, so once we order them for rho itself, and here it's some resulting order. So suppose I have ordered them for rho itself. Suppose they are already ordered. Oh no! Now I put here 1, 2, 3. So here I should change it. Maybe it's a different. So I here do not use this convention. E3, E3. So I ordered them. But now, if I so that was for rho. But then for rho times 0. Probabilities of this state are the same. That is, there are 3 non-zero probabilities. All others are 0. So, and you divide them by the same thing. So you have just precisely. So you have the same situation, and maybe 0, 0, 0, which is not interesting. And then you consider this. But for this, you have the only difference. For this red one, so for this red one, oh no, this is red. What you get for the red one, you just add here W. Yes. So they are all rescaled the same way. So therefore, the order is the same. So the same order. So what is the only difference between these two things? So let's say, so this diagram now, it looks precisely the same as this, but it has so that's the green one. So the same, and also here something not so relevant, zeros for us. So here is Z of the system itself, okay, and here is Z of the system plus work. But this really doesn't matter, because we are this is the where it's non-trivial, the function. Now we consider the second case, and what we have here is that it's the same order, but you see these quantities are smaller. So here they are this original E2 minus beta E. Now here if I extend it, then I have this smaller rescaled for these 3 quantities here. So I should have 6. So it is E2. So it is E2 minus beta E I1. Yes, and so on. And then we have E2 minus beta E I1 plus W. It need not be the case. Yeah, good. But I should finish here. Sorry. Here is Z. Yes, and here I have this further rescaled three rescaled things. So this is E2 minus beta EI1 plus W, and so on. Okay, so these are standard energies, they are energies plus W. So then I should draw also this diagram. But as I said, this diagram differs only by the fact that now these quantities should be on x-axis. So I put this here. And otherwise, this diagram doesn't differ. So it differs only by this additional factor in the denominator, and therefore it's just shrinking x-axis. So, right. So we get that. So we get some fact that F rho times W is equal to F rho times of x, and here is of x times E2 beta W. So this so this is a shrinked version of this diagram, right? So now in this diagram you nicely see what is putting work to the system. Yes, you simply put work means you rescale your diagram by multiplying x-axis by this E2 beta W. Okay, and then therefore you can, knowing this, you can answer all these questions very easily. So let me start from the simplest case. So I want to know how much work I can draw from given state rho. So it means that I want to go from the system, drawing work is I go from system rho times 0, 0 by thermal operations to what? To something that, to Gibbs state, and I want to get work, right? So what I need to draw is, I need to draw this, which is just the original, its original diagram, as I said, because this this diagram is the same as this. So maybe it would be this, and F rho 0 of x is just F rho of x for x's from 0 to z, and 1 for other else. Here I should also add 1 else. Good. So this diagram I know is just the original diagram, and this one is what? Is the diagram of the Gibbs state shifted, like shrinked. Good. So let me draw. So I have my original diagram of rho, F rho, and that's original diagram of tau of the Gibbs state. Now I shrink it by W, so I obtain this. So that's the diagram of tau times W. But look, then this, and I want to go from here to there. So I want to go from green to blue, but I can't because this doesn't majorize this. So there's the first lesson. If my original diagram ends up here, then no work, I cannot draw any work. Which means that, but what does it mean that my diagram ends up here? Meaning it's not all diagrams end up here. But let me just, I want to make a difference between these diagrams versus, so this diagram is here trivial. So essentially I can say it ends up earlier. So what's the difference? So this happens if you have some non-occupied levels. So whenever you have non-occupied level, you are here. So these are two occupied levels and then non-occupied. Here all three are occupied. That means that I can only get work, so that's first moral, can get only if some levels are not occupied. So then you say, okay, in physics it never happens, in reality it never happens. So what you do, you say, okay, you then smooth it. You say, okay, with some I have some levels that have very, very small probability of occupying, and then I risk this with this probability that I failed draw work, and I will later show you that it leads to standard thermodynamics to accept some very small, error. But for a while, let's do everything in a very rigid way. Yes, later we can smooth if you want. So to draw work, we need empty levels. Okay, so let me draw take some row that has some originally empty levels. Right, and now so that's my F row. Then I have here F tau times W. So it is, sorry, it's tau, F tau. Now, sorry, so this should be the original one. Okay, so that's simply F tau, a Gibbs state. And then how much work I can add to Gibbs state in order for my diagram be still below this, so that this is possible. So, so I can go until here. This is the maximum I can do, and then this, because then this diagram is still below that one. Right, so then I have to, so let's then they calculate for the formula for the, so we want find the maximal work such that F tau W is still below F rho 0, which actually it's just F rho. Oh, okay. It's same as saying this. W. Okay, so I need maximum work. So, okay, but I know that this is simply rescaling of the x-axis. So, so how we should then. So what is this thing? So on one hand, this thing is nothing but is z of the system minus this thing. But what is this thing? Well, I rescaled this. To get this diagram, I rescaled x-axis by E2 beta w. So this should be just times E2 minus beta w. Right? So this is this thing. But on the other hand, what's that on the other hand? On the other hand, let's see. So these, let me go. So what are these? These are these Boltzmann factors for occupied levels. Yes, Boltzmann factors for non-occupied levels are here. So here are Boltzmann factors for occupied levels, and so on. So what is this thing? What is this thing? These are Boltzmann factors of all levels that are not occupied. Right? E2 minus beta. So from this we will see that, but this we can write is what? Is the total partition function minus all the Boltzmann factors where you have for occupied levels. Right? So then you cancel this, and you get that E2 minus beta w is what? Is 1 over zs, this thing, times this thing. Okay. Okay, so therefore this maximal, we can write here, this is this maximal that we can do. So this maximal work is what? Is minus kt ln of this thing. But look, this thing together with this thing is nothing but a Gibbs state occupation. So we can write it like this. those i's that pi different than 0, and here we have this. So this is Gibbs state probability. Well, and then everything is a matter of naming it. So people named this thing to be this d mean relative entropy, mean relative entropy. So actually, you see that these are only those i's for which the state is different than 0. So it's precisely trace, and you put here the projector onto rho, right? And then you here put Gibbs state. So it is precisely the minus kt. And if you want to have information theoretic mean relative entropy, then you simply. So it is defined by definition. Okay, why? So you see that these diagrams, this criterion, allows us to compute the maximal work that you can draw from a system. Then you can ask, well, okay, the homework was to compute the minimal work you need to build a system. So I only will tell that if you want to build a system out of Gibbs state, then you add work to the Gibbs state until it is above this diagram. Then you can create rho, because then you can go from your so that was distillation. So that's distillation or work extraction, and now work of formation must be this. So you have to really go above, and then you can have transition from here to there. So you can create rho. So then the homework is to compute what is this thing. What's this minimal work? Now we want to minimal work, right? And this will be also relative entropy of different kind, the max relative entropy. And okay, so now let me go standard thermodynamics. So we know that just not to forget to say how you then compute the work that you can get if you are required to go from rho to sigma. So you have full algorithm here to do that. You simply have some original. You have some original rho. You have some original sigma. Okay, and if you want to go from rho to sigma, you see that you need to add work, because you need to add enough work for the diagram of rho to be above diagram of sigma. So you simply do this, and this is so that this is above. So you have to compute minimal work, minimal such work. So this is not work. It's really E2 minus beta W, minimal W, so that this gives the diagram that's above the original diagram. So you can say that minimal work is equal to what? A minimum of over W of such W that f of the rescaled that f of you started from rho, so you take rho, you rescale it, and that it is still that is greater than original f sigma. So in normal majorization, just compare two diagrams. When the diagrams are arbitrary, but you can then compute how much work I need to go, and then you simply should rescale one of the diagrams. Yes, you rescale one until it's above, until it's entirely above. I do not know some nice analytic. Yeah.
Maybe just like doing this to the Gibbs state and then coming back from the Gibbs state.
You mean if I go from?
Just to calculate the difference, the work difference between what you get from rho to the Gibbs state and the Gibbs state.
So in there reversible theory, yes. So if I do this thermodynamic, the limit when I take many copies, it will be the case. But in this case, it's irreversible. So simply would lose too much in going to Gibbs state. Right. So therefore, here you have this complicated answer. Okay. So now let me see how much time I have. Right. Sorry, I started 10:45. Have it now. Good. Okay, so we have now algorithms to compute everything here. Let us now see how it's related to standard thermodynamics. So you see that here you do not have entropy, yes? You have relative entropy. But standard thermodynamics, it's enough to work with entropy. So we'll see how it will emerge.
So here we are assuming we have only one work qubit.
It's enough, yeah. If you have some bigger work system, you will get the same result.
But we need a deterministic work abstraction. Like
yep.
We don't allow finite probability of occupying the excited state of the work qubit.
This you have to do separately. Yeah. So I will do that in a while. To get standard thermodynamics, I will allow for some small probability of occupying some levels. But I will let this probability to 0, and we regain standard thermodynamics for many copies. For a single copy, you cannot. As Renato said in the end of his talk, if you have a single system, if you have some probability of occupying some level, you have to deal with it. You have to live with it. You have to say, okay, with this probability I will fail. And here we can say the same. With this probability I will fail. With the other I will have some work. But if you have many systems, then you can make nice things. You can let this probability to 0, and you'll get nice formulas, which will be standard formulas. So before I arrive to standard thermodynamics, let me just summarize how nicely you can write. First, quickly, I get standard for thermodynamical formulas. Formula for work extraction. Same you can do for a work of formation. So for work extraction, we simply you can yourself check using So you can define a smooth quantity, which is just infimum over all states that are close to this state, and okay. So this is saying this: if I have a state which has some occupied levels, but these upper levels are very tiny occupances, and they are significant. So these are occupied with epsilon. Then I say, okay, maybe if I'm happy to tolerate error epsilon, then I should compute this work not on my original state rho, but I should compute on some rho prime that is close to rho. So I should compute it where here there's no occupation, and here you have these levels are occupied, and here no occupation. So that's rho. And you are looking for some rho prime that is close to this, but is more favorable. So it has so according to our rigid formulas that I presented to you, this will have nice answer. This will be some non-zero work. While for this, according to rigid formula, the work would be 0. Right? So therefore, instead of taking this rigid, I just smooth it. I just try to find a state which is close by epsilon, but still it allows, but it allows for something, some non-zero work. Okay, and then if one want to be more detailed, you can have a better smoothing which includes the heat bath. here I just applied smoothing directly to the state. But you might consider smoothing that includes heat bath, and this is a different smoothing than so far was considered in this quantum information theory. So in quantum information theory, you just smooth the state. Here you see the state, but you can recall that there was a heat bath, and it will be completely different smoothing. And this is not yet well developed. We just gave some examples in our paper. But it's to get standard thermodynamics, it's enough to smooth this. Right. So this is the definition, and now there is some fact. Simple fact. You just that if you take many copies of your system, then it turns out that this that would be the amount of work where you risk the probability of failure epsilon, but that is still greater than here is standard Kullback-Leibler or standard relative entropy, right? So it's just minus trace rho. Sorry, it's trace rho log rho minus trace rho log sigma log tau. So it's standard plus something small, and this where epsilon is exponentially small in n. Say some constants. So what it tells that if I have many copies and I tolerate error that goes to 0 very fast, then then essentially the amount of work I can draw is proportional. Is just given by the relative entropy of standard relative entropy, right? So, and then but still in standard thermodynamics, we are not very used with using this relative entropy. So let's just go to free energy.
Is this inequality go both ways?
I actually I dig some papers trying to see some smooth formulas. Somehow maybe I should dig more. So this is what cooked for the just cooked out this. There should be much more about this smoothing. But, yeah. Right. So therefore, which.
The proof is typical sequences.
Yeah. Exactly.
So it has to be.
Yeah, but you can then maybe. Because here you have this infimum, so you should ensure that you can ensure, yeah, maybe you're right. Sorry, what is what?
After the inequality sign.
Here?
No, in the fact.
Pact.
This d greater or equal than something.
And
bracket.
It is? This is the number of my copies, and this is the same n. I simply take a very special initial state. Okay, so let me see that it's indeed what we expect in thermodynamics. So let us make a more nicer. So in standard thermodynamics, maybe here. Standard thermo, we know that the work is simply delta F. So the original F is F of rho, and finally is F of Gibbs state. Right? So, but this F you can write as, but it turns out that F rho is equal to F tau plus kt d rho tau. You can just check yourself that is true, and therefore you get that this work is indeed simply kt of rho tau, right? So you have the work is the difference of free energy, and therefore it's this. So we've got just precisely the right answer. And what is then tempting is to think of new free energies. So let me add what we have. So we have that work, extractable work, is this minus kt. So it is the mean. Work of formation is minus kt log 2 d max, which I didn't derive here. That was the homework. So we have these two quantities. And then you say, well, but I should just introduce some free energies. So it should be some delta F min. And it should be delta F max. Okay, and the obvious way to is just that F min is simply of rho, is simply F min of tau plus kt. And now we have the mean of rho tau, and the same for max. And for this we set it equal to F tau. Therefore you, with these definitions, you really get that you have that work is difference of free energies, but it depends whether you want to extract or work, then it's mean free energy. Whether you want to put work, it's max free energy. And these things are different, but so the picture is this. You have irreversibility. So you have this. So this is this work of distillation, which is this delta F mean, F max, work of formation, and somewhere between you have delta F, and then this is work. Distillation is equal to work of formation, but it is in this many copy limit. So let's say many. This is when you have many copies. Yes. So you have standard. This is standard term. Standard. And this is single shot thermo, right? So this is single shot thermo. So in entanglement theory, we are used to the situations that we have some irreversibility, and then if you take many copies, the same copies, you have back to the reversible situation. For pure states entanglement, it's like that. So final remarks are the following. So far, Hamiltonian was fixed. So I didn't change Hamiltonian. So in this picture, it's not natural to change Hamiltonian because we have we imagine that we simply that all these changes go into this U. So what we do with the system is in between, is inside of U. So essentially, I imagine this. I have some system. I have heat bath. I bring the system to interact with the heat bath, and in this interaction, I do whatever I want. And also, I bring this work register. I interact, and then I take far apart. So the big picture is some time-independent Hamiltonian, even because this bringing and taking apart also can be formulated in time-independent fashion. It's like standard quantum mechanics. Everything can be time-independent Hamiltonian, and this time dependence can be formulated as a clock as an additional degree of freedom. But it's nice to be able to change Hamiltonian, just to have much closer, comparison with standard thermodynamics. And we know. So what's the formula in standard thermodynamics? Is this that if we have some Gibbs state tau with some one Hamiltonian, and then we go to Gibbs state with some other Hamiltonian, then the amount of work is just the difference of free energy. So we go from Gibbs state to Gibbs state, and then you get work. So in our case, we wanted to make the Hamiltonian that we can change it, and we mimicked it. So to change Hamiltonian, you need a clock in time-independent picture. So we added a very primitive clock, which will be just 2-level clock. So we added. So our joint system will be Hamiltonian of a system and clock, and it will be initial Hamiltonian plus final Hamiltonian. So that's a clock. and that's a system. So now instead, so our system will now be together system and a clock, and we require that the initial state of the total system is initial times 0, but we require that the output system, the clock is returned in the pure state. So now we do not allow to do anything. Just we require, so clock should be clock. It should be just tell us that, okay, now your Hamiltonian changed. So so you see this is fixed Hamiltonian, but because the initial and final state are different, are of this form, it mimics change of Hamiltonian. This is what really happens. If we write time-dependent Hamiltonian, we really have a clock, and the initial time, the variable here shows us initial and final time, though this clock is very primitive. So and then we gain these nice formulas. So we apply these thermodiagrams to this initial and final. In particular, if rho in is just Gibbs state and rho out is another Gibbs state, then our work is precisely delta F. Right. So it's maybe good to know this thing. In one shot, even in one shot. Yes. That's somehow because somehow you have here, like here you have already the vacancies. This creates you the vacancies. Yes. So the Gibbs state is only here. Yes, and here you have some.
I actually wanted to ask something about the connection to thermodynamics. So, because we earlier defined that by thermal operations we can any non-equilibrium kind of non-Gibbs state we can just move to Gibbs state, and then we introduce this concept of work. But like if we don't use this work qubit, where does this same kind of energy or work or heat go?
Sorry, where
so
if we do not
we have
use
a thermal operation that moves this
then do not use the work system at all.
concave curve and the Gibbs state. So
then it's simply then some energy that was in the state gets dissipated, so it's not so essentially it's to the heat buff, yes, because your initial state is a heat buff, right? So your initial state is some state of a heat buff, yes, and of work, and you don't want to use this. You just want to go. Suppose we want to go just to some. Here you want to go to some sigma, which means that we go to some total state of sigma, and then we will partially trace, right? So then, yeah, then suppose now that sigma is really a Gibbs state. So you just lost everything. So where is this lost stuff? Well, because we did unitarily, then this lost stuff must be somewhere. So it can be in the correlations between these two, or just in the heat buff itself. So simply it could be that this state changed, so this rho sigma r is not anymore a Gibbs one, or there are some correlations between. So it was then like, let's say, stupid to do that. You would better use this energy to put it to store it here rather than just dissipate or hide in the correlations.
Then can I just say removing a certain state or tracing out a certain state actually changes the total energy? Otherwise it should be.
Removing changes how? I don't see.
I mean, like the thermalization changes.
Thermalization. Why it changes? Thermalization. The total energy is well.
Because if you compare the initial energy and the final energy, they are not necessarily exactly the same.
Yeah, but then you have to talk about some average energies. Yeah, then you have, yeah, of course, if you have just some joint system, then the average energies are not related in a very, not necessarily related to nice way to the total energy. And yes, you have also, you should look at the correlations. Yeah, but I don't think we care here about these things. So that was the point. So normally, so there were some papers where people say, oh, we violated second law because we had some non-Markovian coupling, and then you can violate second law. So when you go to these papers, you may say, because they have wrongly said what is really the work. So some energy that was still present in the correlations. They thought that this is the work they have drawn. So in all such perpetuum mobile papers, yes, you may try to see why, what was wrong in their understanding of work, yes? And here we just wanted to prove that you do not have any such perpetuum mobile, not by just looking into particularly what you did wrong, but say I allow it to do everything, but the work should be this. Yeah, so you can really do everything you want, whatever coupling, normal covariance, something completely ridiculous. But later, I want to see whether in my work register I got this work or not. So essentially, it's this thing to be really model independent by having clear definition of what work is.
My question was in the thermodynamics. There was a concept of heat Q.
Uh-huh.
That is transferred to reservoir and back. And is there a similar concept here?
So here you essentially should get heat by just I think by just subtracting the original energy and the work. So just this. So here heat is not any. Yeah. So we even didn't do that. But you can you get it from you should get it from simply first from first principle, so from conservation of energy. Yeah. Yes. Sorry, isn't the heat?
You borrow give state from your heat bath and bring them back with more or less energy.
Okay. If you wish here, you can really think you have just single heat bath. You have heat bath. You do, for these derivations, I didn't borrow the Gibbs states. Essentially, I have one big heat bath, let it interact it, and then so I don't see how to follow your concept. Yeah. Yeah. So of course there was some change to the heat bath, so something flowed there. Yeah, it could be like that. So if you do any transformation, you dissipate some energy to the heat bath. So, but to compute how much, you simply have to subtract, I think, the energies that you had. You have to simply see what was the change of energy and say, aha, I do not have in my system this energy, so it must be heat flow there. So, but we didn't do that actually. So good. So my final remarks are the following. I couldn't have time to tell about this further developments and a little bit different definition of work using the change of Hamiltonian. So let me just say, just in 2 sentences, very roughly. So so here we're paranoid. We have access to whole heat bath. While you may think, like Johann Aberg did, where you simply have your reservoir, you have your system. Here you allow only thermalization, meaning you simply bring your system to the heat bath. Put it to the heat bath and it just becomes thermal. So only thermalization. But in addition, he allowed this change, cyclic change of Hamiltonian, and was careful about accounting for work. So he insisted that the probability of getting work is peaked. So then we say, oh, I have almost deterministic work. I have finished. Okay, good. So that's this. And so that looks like very crude operations. And then he get the same formula as ours. So he got essentially, but here you necessarily have to have smoothing because this you get work still probabilistically with some tails that you then say, okay, I failed, and then you are almost deterministic work here. So you have smoothing to begin with. So you have he had this, that work is equal to this thing. Then in next paper so that was done in the same time independently. So simply we worked independently and got the same results. That was really fun. And then there was later paper by Egloff et al. Who did this? So here they allowed all thermal operations. So they allowed all thermal operations just for state change, not for join work. And here change of Hamilton. Okay, here change of the same change. And they got the same formulas as they get the formulas that are the same as we got from this algorithm that I showed you that we obtained. And so what is still, so this is still, I say, not finished, because while this is very nice, this is just thermalization. So everybody would agree that that's you do not need to know anything about thermals. Thermal bath. You just put it to the bath and take back. While here they require thermal operations, so it is still very paranoid. Like okay. So you would like to make this less more crude, requiring much just some weak coupling, some standard coupling. And I think we are trying to do that, and we think it's impossible. We think we at least have to have a bit of memory, meaning a bit of control of at least some part of the heat bath. Good. Okay, I have how much time? Some negative amount. 5 minutes, right? So then there is a next story which is which nullifies everything I told you. Namely, there is this embezzling phenomenon that was there is paper by Patrick Hayden and Wim van Dam, which also kind of nullifies the entanglement theory. It simply says that you shouldn't do any resource theory because you are going to have trivial theory, unless, and I do not have a good solution to that actually. So still there is some work needed. Namely, you simply in entanglement theory, you know there is the phenomenon of embezzling that if you have some entangled state, then you and you want to go to some, or even entangled, you just have nothing. You have some product state which has no entanglement. Then you add some other state. This is called, say, embezzler. I don't know, embezzler. So this will be, and then you can make a local transformation. So this is a transformation we cannot bring an entanglement, and then you end up with your favorite entangled state here, with something that is almost, and your embezzler back. Almost, and this error actually, it's a good scaling. So meaning that you do not need really large dimension to make to get to this for this epsilon to be small. So so this is related to catalysis. Yeah. So you have some catalyst, you put it, and then you get it back, and from nothing you got something. So this essentially, and this phenomenon you can apply to this whole theory. So you just let's consider this Planck's law, Planck's Kelvin formation of law, that without any change. So if I didn't do any change in the environment, then I cannot draw work from the heat bath. So what is the meaning of not making any change in the environment? It means that you could operate on the environment, but you should then return to the original state. Okay, so if we are so careful that we return the environment to exactly the same state, then this cannot happen. And just you and you can try. So what will happen? So we did the job, and we considered this scenario where you allow to add catalyst, right? So and we obtained that then the whole thermodynamics is not governed anymore by the diagrams, but it's governed by Renyi entropies, relative entropies. So it's in the paper by Fernando and others. Brandau. Good. But then, if you allow your environment to be returned in some not exactly the same sense, but a little bit different, then you get everything trivial. You can get everything from nothing. Like from a Gibbs state, you can draw work, all these things. So, but you even didn't need this a little bit sophisticated, although extremely nice blue proof that is given. You just consider the following situation. Suppose you have a state which is which has this level not occupied, and here equal occupation. And suppose these are energy levels, equal energy levels, right? So that's the initial state. Then you go to the output state, which is this. Zero. So these states are extremely close in any measure of any fidelity measure, any norm. That is useful, like the trace norm. Namely, the distance is just 1 over d. So if d is large, then it's just completely disappeared. But now you see, going from here to there, you clearly get this amount of pure energy. Yeah, you can just take this width and make and you can take this system and the width, and you lower this and you raise the width. Some two-level system. So already here you see that that you cannot really use such quantities like you shouldn't use the distance that is. You should measure error. You should measure error in using standard distance fidelity or whatever. So now on this paper we propose some other ways of doing that, but still there is a challenge how to do it in a nicer way to avoid triviality. So simply not to be killed with this or this phenomena, and to get thermodynamics from some very basic assumptions, rather than in some model independent way. So I think I will thank you.